I realize that my chicken scratch is going to be difficult to see, but this information is available in your machinery's handbook, and it's also available all over the internet. So I'm going to do an FEA analysis on a cantilever beam. And for this particular problem, I'm going to use inch-pound-second units. For later problems, I'll also use metric units. I have a beam that is a square 1 inch by 1 inch square and 24 inches long. My material is mild steel with these properties of elasticity, yield strength. Load will be a 150-pound load on the right side end, with a fixed constraint on the left side end. If you do the hand calculations, and again these are in the machinery's handbook, I come out with a hand calculation with a displacement of 0.272 inches. I get a calculation of the stress, 21,600 psi, and a calculation of the safety factor of 1.4. Let's set the problem up in SolidWorks. The first thing I did is I selected a material, and I selected plain carbon steel. I set my material properties in inch-pound-second units, and the material properties are slightly different. If we round this off, this is essentially the same number for the modulus of elasticity. The yield strength is slightly higher, but we should be in the same ballpark, and later on we'll see how to create our own custom materials to some exact properties of whatever we're given. So we'll go ahead and accept that plain carbon steel as our material properties. I'm going to change the background to white. Let's assume that we are going to print this on a white sheet of paper, and we don't want a shaded background, we just want a plain white background. So then I'm going to start a new sketch on the front plane, and I'll draw a rectangle to the right of the origin, and then I'm going to put a midpoint constraint between the vertical line on the left and the origin. I will then put some dimensions on here, so let's dimension this as 1 inch, and we'll put our 24-inch dimension for the length. Then I'm going to extrude this, so I'll go to my features and I'll do extrude, and I want to go mid-plane. I'll make the extrusion distance equal to this 1 inch sketch parameter. I then need to make sure that I have my analysis tools loaded. So I'll go to add-ins, make sure that SolidWorks simulation is loaded. I'll then go to the simulation tab. I'll select new study. We're going to do a linear static analysis, so we'll just leave it on default. We've already applied our material, but if we wanted to check with different materials, we could just copy this study and then put in different materials that we want to do for each one of those copies. So I could right click here and tell it to copy that study, and then using the same part, different materials. Now there are some advisors in here that will walk you through the process of what you should do. We're just going to go ahead and put the appropriate constraints and loads on our part. So I'm going to do a fixed geometry constraint, and I'll put that over on this left end. Then I'm going to go to the loads, and I'll put a force load. I want to put that force load on this end, but I want it pointing down. So I'm going to do selected direction, and I want it perpendicular to this face, so I can select this face or this edge to define the direction. And then I want to put in my units as inch-pound-seconds, and we're going to do normal to the plane, and we'll do 150 pounds, doing normal or perpendicular to this plane going down. Now we won't include gravity in this analysis. On this small part, gravity is going to have only a minimal effect on it, and we want to, later on we'll do some more complicated or larger parts where we will include gravity. I'm then going to go over here to where it says run this study, and I'm going to click this down arrow and select create the mesh, and I'll just leave it on the default settings for now. Later on we will adjust the mesh. So I see that we have a finite number of mesh elements created with tetrahedrons, and we'll discuss that more as we get further along in the class. So I'll go ahead and tell it to run this study, and so here we see our results. We can drag this window around to put it in different locations. I like to put it up here. Our units are given in newtons per meter squared, so I want to change this to inch-pound-second units. Double click on color bar, and then I'll come down here and I'm going to tell it to give it to me in floating notation to 3 decimal places. I'll go to the chart options tab. I'm going to select it as KSI. So we could do it as PSI, pounds per square inch, or thousands of pounds per square inch. I'm going to do it as KSI. Notice there's also a deformed shape setting here, and so we could tell it to do a true scale deformation or user defined, or leave it on automatic. SolidWorks is automatically going to exaggerate the deformation so that we can clearly see where it is occurring, and that's one of the most common issues that people on the internet post questions about, that they get confused with, is that they say, I know my part doesn't bend that much, because this deformation has been exaggerated so we can clearly see it. Alright, so now I see that I have a stress value of 21,600 KSI, thousands of pounds per square inch, and our calculated value was actually 21,600, our hand calculation. So even though our material properties were not quite the same the way we set it up, we are in the same ballpark with our evaluation. If we were to make 20 beams out in the real world, if we made 20 beams and we tested those 20 beams, physically tested them, we would see a variation, a slight variation between those 20 beams. So we're looking for ballpark numbers, not a 2 + 2 = 4 type of number. If I go to the displacement, I see the displacement is given in millimeters. I would rather have this in inches for this problem, so I'm going to double click. I'll go to the definition tab, set the units as inches. We'll go back to chart options, and for the color bar chart I'm going to set this to floating, and we'll do to 3 decimal places. And so on our hand calculations we said 2.272 inches, so we get exactly the same value in the analysis that we have for our hand calculation. I also want to display the safety factor, so I'm going to right click on the results and I'm going to say define factor of safety plot, and I'll leave it on automatic. I'll say OK to that. Now I'm not sure why SolidWorks does this, but it shows you from the minimum factor of safety, and we calculated 1.4. SolidWorks has given us 1.5, so we're in the same ballpark. We want to be safety factor above 1. We're still within the elastic range, the linear elastic range of deformation. We haven't gone into nonlinear plastic deformation. I want to though change this factor of safety color bar. It doesn't make sense to show really the maximum safety factor on this. If we have a safety factor greater than say 15, then we know that that is perfectly fine. And so I'm going to change that. I'm going to go to the settings tab. I'm going to go to chart options, and I'm going to uncheck this automatic define maximum value, and so I don't care about anything over some value, let's say 15, and I want to see I want to put then the minimum value at 0. Now we want our minimum value, we want it to be greater than 1, which we are, 1.4, but for our chart options let's set 0 as the minimum value. Sometimes SolidWorks will automatically check mark this box, which will turn everything red here. Make sure this box isn't check marked, and so I'm going to do then this as floating, and I'll do 1 decimal place on the resulting value. I'll say OK to that. So again, our minimum factor of safety is 1.5. so that is analysis in SolidWorks comparable to our hand calculations.